3I. Atlas didn't vanish from the universe. It slipped out of the thin slice of reality our cameras are capable of seeing. For a few brief nights, the object is there, a jittering speck on a survey image, barely brighter than the background noise. Astronomers mark it, calculate an orbit, schedule follow-ups, then, in frame after frame, it simply stops appearing. Not because it exploded, not because someone turned off a telescope. It disappeared the way a whisper disappears in a stadium, by being drowned in everything else. From the first alert, 3 constraints are already closing in. The object is faint, riding the edge of what our detectors can register. It is fast, crossing pixels between exposures faster than algorithms expect. And it is fleeting, visible for only a narrow window before geometry and sunlight shift against us. Together, those constraints ensure that the smallest change in conditions can make a real thing look like it never existed. Picture one of the last clean nights. A survey telescope takes a long exposure as 3I. Atlas races through the frame. Thin clouds add scatter to the starlight. The object's light smears into a dim streak. To human eyes, the frame still looks like stars on black. To the pipeline that sorts thousands of images a night, the streak falls below threshold and is deleted. The log will never say mystery visitor erased. It will say nothing at all. In everyday life, this would be like trying to spot a single unfamiliar car in a time lapse of a whole city. Traffic lights flare, reflections smear across wet asphalt, and compression throws away details it decides you don't need. Somewhere in that blur, the car passes once and is gone. Later, when someone insists that car was important, the footage cannot prove them right or wrong. It only shows the limits of what it was built to notice. Online, that silence acts like an accelerant. Screenshots of the last detection circulate with captions about the object they don't want you to see. The gap between frames is treated like evidence that something dramatic happened off-screen. But the real story is quieter and more unnerving. The universe is not staged for our cameras, and most of what passes through our neighborhood will slip by undocumented. And that's where the real problem begins. Because if an object this close can fall through our instruments, it forces a harder question. How much else is moving through the dark, perfectly real and practically invisible, while our technology keeps telling us the sky is empty? This channel is inspired by Dr. Michio Kaku's Public Ideas, but this episode is independently written and hosted. Before it disappeared from cameras, 3IATLAS was already an edge case guest in the solar system. It is not a spaceship, not a secret weapon, and not a coded message. It is an interstellar object, a piece of rock or ice that does not belong to the sun, simply passing through. Its path is hyperbolic, meaning the arc of its orbit never closes. Once it dives through the inner system, it will never loop back for a second pass. That alone makes every hour of observation non-renewable. Interstellar visitors arrive fast. 3IATLAS crosses space at tens of kilometers per second, not because it is powered, but because it has been falling through galactic gravity wells for millions of years. Against the slow drift of background stars, that speed turns it into a moving target that refuses to sit still in any one patch of sky. Telescopes built to catalog predictable, slowly shifting asteroids suddenly have to track something that behaves more like a thrown stone than a planet. Size makes the problem worse. This is not a glittering world with ice caps and clouds. It is small, likely only a fraction of a kilometer across, with a surface that probably reflects less light than fresh asphalt. To show up cleanly on a detector, it has to be close enough, bright enough, and favorably lit by the sunday. For most of its flight, 3IATLAS is none of those things at once. Brightness is not just about distance. It is about geometry. As the object approaches, the angle between the sun, the object, and Earth changes constantly. Sometimes the surface reflects light straight toward our instruments, and the object brightens for a short, glorious stretch. Sometimes the light skims past, glancing off into space, and the object fades toward invisibility, even as it gets physically closer. Now, layer this reality onto how surveys actually work. Telescopes scan in strips, night after night, painting narrow bands of sky rather than staring at a single point. If 3IATLAS spends only a brief time inside those strips, and its brightness is sliding up and down as the angles change, then the chance to see it becomes a narrow, shifting slot in time. And that is the quiet, uncomfortable truth woven into the mystery. 3IATLAS did not have to do anything exotic to disappear. It only had to be what it already was: faint, fast, small, and passing through a universe that never promised to make itself easy for human eyes. A deep space camera is less like a human eye and more like a factory line that throws away most of what it makes. To understand why 3IATLAS seems to vanish, it helps to strip away the romance around telescopes. In practice, they are industrial machines for counting photons. A mirror gathers faint light from the sky and focuses it onto a grid of tiny wells on a sensor. Each well counts how many photons land there during an exposure, then turns that count into a number. Stack millions of those numbers, and you get a picture. But that picture is already a summary, a compromise between sharpness, depth, and time. For slow, steady targets, this system works beautifully. Distant galaxies barely move relative to the stars, so astronomers can afford long exposures that gather light until the image is bright and crisp. 3IATLAS plays by different rules. It is small, faint, and moving fast across the sky. During a long exposure, its light does not pile up in one pixel. It smears. That smear can look like noise, a scratch, or the ghost of a satellite trail. Algorithms trained to discard artifacts may quietly erase the very thing everyone is desperate to see. Then there is cadence, how often a patch of sky is reimaged. Survey telescopes do not stare at one interstellar visitor all night. They sweep. Their job is to cover huge areas of sky, over and over, to catch anything new that moves. This means they trade continuous attention on one object for broad, shallow coverage of many. 3IATLAS races through these scanning strips. If the cadence is a little too slow, it might only show up cleanly in a handful of frames before slipping out of the survey's search pattern. Even when the data are captured, they enter another gauntlet. Software sorts detections into real and false. Cosmic rays, hot pixels, and random noise spikes all mimic tiny points of light. To keep the system from drowning in false alarms, the filters are ruthless. Borderline detections are treated as junk. In a catalog with millions of entries, a marginal object like 3IATLAS lives right on that knife edge. And that is where the visibility trap tightens. Every engineering choice, exposure length, cadence, filtering was optimized for a certain kind of sky. Interstellar visitors sit at the fringe of those assumptions. So when people say they lost it, the uncomfortable reality is simpler. The system did exactly what it was designed to do. And in doing so, it erased the most interesting thing in the frame. The same rock can look 10 times brighter or nearly invisible just by sliding a few degrees around the sundae. 3IATLAS never changed its fundamental nature in the short time humanity watched it. What changed was the geometry. In deep space, brightness is less a fixed property and more a negotiation between 3 points: the sun, the object, and the observer. Shift that triangle, and the amount of reflected light that reaches a telescope can rise or crash into background noise without the object doing anything dramatic at all. Astronomers call this the phase angle, the angle at the object between the Sun and Earth. When that angle is small, the object is almost full, like a bright full moon. Sunlight strikes the surface and bounces roughly back toward the observer, maximizing reflected light. As the phase angle grows, less illuminated area faces the observer. Shadows lengthen, contrasts sharpen, and the overall brightness falls, even if the distance stays nearly the same. For something like 3IATLAS, the effect can be severe. Small, dark bodies often have surfaces that scatter light unevenly. Some patches might glint, others drink in photons like charcoal. At certain angles, the scattering pattern lines up so that very little light is directed toward Earth. In a catalog that plays out brutally, 1 week the object sits a hair above the detection threshold, the next week it slips a hair below it, and the pipeline writes it off as gone. Orientation adds another twist. If 3IATLAS is elongated, tumbling slowly as it flies, the cross-section it presents to the Sun and to Earth changes over time. On one rotation, it might flash a broader face, bright enough to register cleanly. Half a rotation later, only a narrow edge is lit and visible. To a survey with fixed exposure settings, that can make an object flicker in and out of visibility, even during a single campaign. Now combine that flicker with a scanning strategy from earlier parts. The sky is not watched continuously, it is sampled. If the sampling happens to hit during a dim phase, bad angle, narrow profile, unhelpful scattering, the camera tells an honest story. There is nothing significant here tonight. From the standpoint of raw data, that is true. From the standpoint of reality, the rock is still there, moving, indifferent to whether it is briefly promoted or demoted by human instruments. And that is where the real problem begins. Because once brightness becomes a function of geometry and timing, disappearance stops being a rare event and becomes the default, unless humans redesign their surveys to assume that the most interesting visitors will almost always be the ones that barely show up at all. The universe doesn't schedule itself around one dim rock, but human suspicion often assumes it should. Behind every dramatic disappearance is something far less glamorous, a spreadsheet of telescope time. Big survey instruments are oversubscribed. They are booked months in advance to chase supernovae, track near-Earth asteroids, map dark energy, and monitor variable stars. 3IATLAS is one line item in a vast queue. When it first appears, it jumps the line briefly. After that, it has to fight for every additional exposure. Earth itself adds strict rules. A ground-based telescope can only observe at night, in good weather, with the object high enough above the horizon to avoid thick air. Clouds, humidity, or high winds can shut an entire night down. The planet rotates, dragging the observatory away from the target. Even in perfect conditions, a given object is accessible for only a slice of the night before it sets or sinks into dawn. Now fold in the object's own motion. 3IATLAS does not patiently hover where last seen. It races along its hyperbolic path, rhythmically slipping into worse geometry as days pass. There is a window where it is bright enough, high enough, and favorably lit. Miss that window, and each subsequent night becomes harder. The same exposure time that once yielded a clean detection now produces only a ghost. To recover it, astronomers would need longer exposures, different filters, or a different telescope entirely, resources that may already be committed elsewhere. The result is a familiar phrase in minor body catalogs: lost to follow-up. It sounds ominous. In practice, it means no one could secure enough additional observations to keep the orbit pinned down. The object fades, its predicted path balloons into a wide uncertainty cone. And after a while, even if a telescope pointed in the right general direction, it would not know which faint speck to test. Seen through this operational lens, 3I, Atlas doesn't vanish. It simply slides off the tight schedule humans have imposed on a chaotic sky. But once those mundane gaps are translated into social media language, the tone changes. Normal weather delays and cue conflicts turn into "they stopped looking." A routine loss to follow-up becomes "they shut the cameras off." And that's where the real problem begins, because the more tightly controlled and resource-limited our observing systems are, the easier it is for ordinary scheduling decisions to be repackaged as proof that someone, somewhere, is hiding the most interesting thing in the sky. Every time the data pause, the internet rushes in to finish the story. When astronomers say an object is lost to follow-up, they are describing a bookkeeping failure, not a cosmic conspiracy. It means there were not enough new observations to keep tightening the orbit before the object faded beyond reach. In technical reports, this is mundane, almost boring. But once those same words migrate into screenshots, captions, and out-of-context posts, they begin to mutate into something else entirely. The last clean images of 3I, Atlas, become symbolic relics. They are shared and reshared with arrows, circles, and dramatic filters, treated less as measurements and more as proof that a mystery once stood here. The missing frames after that are reinterpreted as active suppression. If there are no new photos, many people do not assume that the object simply became too faint or shifted into a bad geometry. They assume someone chose not to look, or worse, chose to hide what was found. Psychology does most of the heavy lifting. Humans are pattern engines. When a timeline shows detected, 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 nothing, it feels like a narrative beat, not an artifact of scheduling and brightness thresholds. The brain quietly fills the blank with intention. If a viewer already suspects that space agencies are hiding something, the gap functions like a blank check they can write any story on. The data pipeline itself, with its automated filters and opaque flags, accidentally feeds this process. Catalog entries that say "no further observations planned" or "orbit uncertain" look like decisions rather than limitations. Technical plots of brightness versus time, with error bars and upper limits, are hard to read. Viral posts trim away the nuance and present a stark cinematic line. The object appears, and then the line goes flat. From a scientific perspective, this is a visibility trap inside the human mind. When information is scarce, suspicion feels safer than uncertainty. A story that blames deliberate concealment is easier to hold on to than a story about underfunded surveys, bad weather, and the brutal math of faint targets. The universe becomes a stage, someone becomes the villain, and chance alignment of constraints is rebranded as intent. And that is where the real problem begins. Because the more often these ordinary gaps are misread as cover-ups, the harder it becomes to have an honest conversation about what our instruments truly can and cannot see, and what it would actually take to do better next time. Even if humanity built a custom probe for 3I, Atlas, that ship would still be flying half-blind. Engineers would start with ambition, give the spacecraft a powerful telescope, agile thrusters, and a guidance computer tuned specifically to chase one fast, faint intruder. Feed it the best early orbit estimates, light curve models, and predictions of where 3I Atlas will cross the ecliptic. On paper, it looks unbeatable. A hunter launched into deep space with a single target and no distractions. But the trap begins with those estimates. They are built from the same sparse measurements that already struggle to keep the object in ground-based cameras. A tiny uncertainty in position and velocity balloons over millions of kilometers. By the time the probe arrives in the predicted intercept zone, 3IATLAS might be tens of thousands of kilometers from where the guidance computer expects it to be. Close on a solar system scale, but effectively invisible inside a narrow telescope field of view. So the designers try to compensate. They give the probe wide field sensors to search the sky around the prediction box. That creates a new trade-off. Wide fields are shallow. They see a large patch of space, but only down to a certain brightness. Narrow fields are deep. They can dig out the faintest ghost of an object, but only in a small slice of sky. The spacecraft has to choose, moment by moment, between seeing a lot and seeing deeply, never both at once. Then there is bandwidth. Every image sent home costs power, time, and precious data rate over billions of kilometers. The probe cannot simply stream raw video of the entire search volume. It must compress, downlink selectively, and often run onboard algorithms to decide which frames matter. In other words, it inherits the same filtering problem as Earth-based surveys, just inside a different metal shell. Latency finishes the trap. By the time ground teams receive the latest images, process them, update the trajectory, and send new commands, hours or days have passed. 3IATLAS, if it was in frame at all, has already moved on. The probe navigates on delayed truth, steering based on where the target was, not where it is. In that gap, an entire interstellar visitor can pass by unrecorded, and that is where the real problem begins. Because even our most focused, high-tech attempt to stare down an object like 3IATLAS is still constrained by the same physics of motion, light, and information delay that made it vanish from our first cameras on Earth. Every generation has its impossible object, and most of them quietly downgrade into ordinary physics once the data improve. A century ago, telescopes hinted at dark, thread-like markings on Mars. Through blurry optics and turbulent air, they looked like straight lines. Maps were drawn, stories formed about engineered canals and dying civilizations. In reality, those lines were artifacts, optical illusions born from low resolution and a brain eager to connect scattered dark patches into something neat and linear. The mystery dissolved not because Mars changed, but because the lenses did. Before that, astronomers believed there was a hidden planet inside the orbit of Mercury. They called it Vulcan and blamed it for the strange wobble in Mercury's motion. Observers reported tiny dots crossing the sun, convinced they had glimpsed it. Decades later, general relativity rewrote the rules. Mercury's orbit made sense without any extra planet. The supposed sightings faded into footnotes about wishful thinking and noisy data. In the modern era, the pattern repeats with more sophistication and faster Wi-Fi. A peculiar comet brightens and dims in an unexpected way. A star's light curve dips in odd patterns. An interstellar object, like Oumuamua, shows a non-gravitational acceleration that refuses to fit the neat category of normal rock. Each time, there is a window where the data are thin and the imagination is thick. Exotic models rush in to fill the gap. Megastructures, alien sails, engineered probes. What actually happens, more often than not, is quieter. Instruments improve. Observations stack. Theories are tested, bent, and sometimes thrown out. A strange dimming star becomes dust and disks, not a Dyson sphere. A weird trajectory becomes a natural outcome of tumbling geometry, outgassing, or surface properties that were not in the textbooks yet. The cosmos did not need to bend its rules. Humans just needed more pixels and better equations. Here is the pattern interrupt. The real anomaly is not that objects like 3IATLAS seem to disappear. The real anomaly is that from one small planet with a thin atmosphere and a cluttered low orbit Humans can see as much as they already do. Every survey image is a miracle of precision stacked on top of imperfect weather, spinning Earth, and limited budgets. And that is where the real problem begins. Because once history shows how often mysteries shrink under better measurement, the disappearance of 3I, Atlas stops looking like a cosmic message and starts looking like what it really is. A stress test of how narrow, fragile, and incomplete our current view of the universe still remains. 3I, Atlas doesn't expose a cover-up, it exposes how small our keyhole on the universe still is. Every step of its brief visit traced the edges of what human instruments are good at seeing. Survey telescopes excel at slow movers and bright bursts. 3I, Atlas was neither. Data pipelines excel at rejecting noise. 3I, Atlas lived uncomfortably close to that noise. Scheduling systems excel at distributing scarce observing time. 3I, Atlas needed more than its tiny slot could ever offer. In every part of the chain, the object sat just outside the center of what the system was actually built for. This is selection effect in action. The sky is full of motion, but only a subset of that motion ever becomes numbers on a screen. Humans design instruments with specific targets in mind. Near-Earth rocks of a certain size, supernovae of a certain brightness, galaxies at a certain distance. Anything that deviates too far from those design assumptions is less likely to be noticed, tracked, or remembered. Interstellar visitors are not just rare, they are misaligned with the filters. From a psychological point of view, that feels intolerable. When something slips away, the story most people reach for is not our systems have narrow settings, it is someone must have narrowed them on purpose. If the catalog doesn't show new data, it is easier to believe that data is being hidden than to accept that it was never captured in the first place. The visibility trap becomes emotional. Absence looks like agency. Science treats that absence differently. A missing object is a measurement failure, a clue about where the detection envelope ends. The fact that 3I Atlas dropped below the threshold is not just frustrating, it is diagnostic. It says something specific about cadence, sensitivity, brightness models, and the geometry of the orbit. For engineers, we lost it is not the end of the story. It is the beginning of a redesign brief. This is the real lesson encoded in the disappearance. The universe did not wink at humanity and close its shutters. It simply kept behaving according to the same rules. While one small civilization tried to watch too much sky with tools tuned for convenience and cost. And that is where the real problem begins. Because until those tools are rebuilt with interstellar visitors in mind, the next 3I Atlas may rush through the solar system, leave a handful of shaky detections, and vanish into the same familiar, human-sized blind spot. The most important thing about 3I Atlas is not that humanity lost sight of it, but that its brief trace left a blueprint for how to see the next one better. In control rooms and conference calls, the disappearance becomes homework. Astronomers and engineers retrace every step. Which telescopes saw it first, which missed it entirely, how the brightness models diverge from what actually happened. Each gap in the record turns into a requirement. Higher cadence here, deeper sensitivity there, faster data sharing everywhere. The vanishing dot on a handful of images quietly evolves into a design document for a different future sky. That future is already being sketched. Wide-field survey telescopes promise to scan the sky more often with sharper sensors and smarter pipelines. Instead of throwing away borderline detections, new systems can flag them for rapid follow-up, cross-check them between instruments, and push them into global alert networks in minutes instead of days. Space-based observatories can sidestep weather, monitor tricky geometries near the sun, and fill in the blind spots left by ground-based sites chained to night and cloud. Hardware is only half the story. The other half is how humans respond to gaps. In a better version of this story, a fading 3I, Atlas does not spark accusations that they turn the cameras off. It sparks a wave of curiosity, public pressure to fund better surveys, build more open data portals, and invite citizen scientists into the hunt. Suspicion turns into participation. The same hunger for answers that once fed speculation becomes fuel for more instruments, more sky, and more truth. Zoomed all the way out, 3IATLAS is a small rock on a long, indifferent orbit. It did not choose to be mysterious. Its path through the solar system was just a brief crossing of two moving systems, one of stone and ice, one of glass and silicon. For a moment, their capabilities overlapped. Then the alignment slipped and the rock continued on while the cameras fell behind. And that is where the real problem begins, because the universe will not slow down to match the pace of one species' technology. Interstellar visitors will keep arriving on their own schedule. Some will be brighter, some stranger, some faster than this one. The open question is simple and unsettling. By the time the next outsider sweeps through our sky, will humanity still be staring through the same narrow keyhole, or will it finally have built a window wide enough not to blink at the wrong moment?